project is location-based microphone management. I'm Kalen Brown. This is Mike Carraher. This is Jacob Starr. And Matthew Cook. Next slide. So I'm going to talk about reasons for why we decided to come up with this project. The general purpose of the project is that it will track the performer's location and it will mute the microphone whenever they get farther away from the microphone and turn it on when they get close. And it will move the microphone to point wherever the performer is. This project tries to fill some industry gaps where there are things in place now that don't quite get the job done, and I'm going to talk about that on the next slide. So sound engineers are people that run this piece of equipment. They run the microphone's volume, mute them, try and make them sound better. Their goal is to keep everything muted and quiet when there's nothing going on, and then when someone walks up to the microphone, they have to unmute the microphone, turn it on so that when someone talks, you can hear them. And if they forget or they're not nearby, then they walk up and then there's no sound that comes out. So the sound guy could be doing anything, but he's not paying attention or he can't get there fast enough. So they've come up with things called audio gates, and what they do is anytime they pick up there's a sound, then they say, oh, well, someone's talking, I need to unmute the microphone. So they turn it on and you can hear. And then when there's no sound, they mute the microphone. And they set the threshold of the noise level so that if there's some background noise, then it'll mute that. But if there's anything above that threshold, then it turns the microphone on. Problem is, there might be a drum kit behind the lead singer, and they'll be not singing yet, but the microphone will pick up the noise, turn it on, it's a false trigger. There might be crowd noise, bands playing, anything like that that might trigger it when it's not supposed to be. There are some things that do this based off of distance already that will mount to the microphone, and they will pick up how far away the person is and then mute it or unmute it based on how far they are and a threshold. But you have to change the threshold on the microphone right here. So if you do it wrong and you set it too close, but the person's back here, it won't turn the microphone on, and there's nothing the sound guy can do to change it because he's back in the back of the room and he can't go change this. So that would be remote control. And like I said, there's no way to bypass it, so it's always in there. It may ruin the performance. There is some vertical microphone positioning, so if someone walks up and they're taller or shorter, you can raise or lower the microphone, but there isn't presently anything that turns it left or right. So that if I'm over here, it'll point the microphone at me to pick me up better. So ideally, the users of this project would obviously be a sound engineer that could use this and set it up properly and maintain it, run it, keep an eye on it the whole time. That person might be running live sound like a concert, or they could be the sportscasters at the football games. Could be TV stations, anything like that. Anytime anybody gets close, all those kind of things. You could also mount it permanently and have all the settings preset and then leave it mounted, and then a general public user wouldn't have to plug in anything and they could use a touchscreen like normal. Right. And we're going to go to Jacob.
And today I'll be talking about the goals, the standards, and the assumptions. So our first goal is a customer-centric goal, which says that by October 25th, we aim to produce a smart microphone stand that will be able to rotate at least 90 degrees to the point where the microphone will face the user. This includes a wireless circuit, which will unmute the microphone within 1 second. It's okay. When it's detected that the user is in front of the microphone. So to measure this, we've been using a rotation range that we measure in degrees, proximity array range, which is measured in feet, and we have our delay, which is in seconds. So our goals, we are measuring the degrees with a protractor, and the range is measured with a tape measure, of course. The delay is measured with the internal Arduino clock, the stopwatch on it, and then the observation of the end user interacting. For our objectives, we are designing a mute circuit that is essentially using a relay to short the hot nickel wires on the XLR cable. We're designing a separate motor control able to turn the stand for a total range of 90 degrees. And we're designing a proximity sensor array that's able to compare the proximity values to determine the user's position based off of where they're standing in front of the microphone. So our next constraint is for health and safety. So at the end of the project, all of the components should be completely enclosed to help protect the user and prevent electric shock. For our manufacturability, by the end of the project, the battery on the remote side of the project should be able to last at least 5 hours on a single charge. And our sand is what we're using for the weighted bottom for the box. Our environmental constraint, we said that by the end of the project, the weight of the remote side and of the user side should not exceed 10 pounds. And we also wanted to make sure that our project was ROHS compliant. Our economic constraint said that by the completion of the project that we should not exceed $550. So for technological constraints, we wanted our proximity sensor to be due by September 20th, and our mute controller also to be due by September 20th, including the hardware and the software components. We wanted our comparator to be finished by October the 4th. We wanted our user interface to be also finished by October 4th. We wanted all of the power supplies, including our backup power supplies, to be finished by October 25th. And then our system manager was due by October 31st. And for resources, we have a plethora of available resources to us. And we also have available time in the 3D printing lab to print out our sensor manager and also the cover here for the screen. For our physical constraint, we have a maximum weight of 10 pounds that we did not want to exceed in our project. Some of our standards, we're using the 802.15.4 with our wireless communication, and we're using safety, which uses that standard. The difference is that it has additional routing functionality and it has additional networking functionality with the safety protocol. And then for our assumptions, we have a fixed podium and presenter height range, which, said we could always adjust it manually, but we're assuming that they're not going to change height while they're on stage. Our second assumption was that the microphone and the soundboard are in place. We assumed that the power on the soundboard end was present, and that we have our XLR microphone connections instead of 3.5 millimeter. And now I'm going to take it to Matt.
So whenever we started out this, we came up with several different implementations that could actually successfully complete this project. When we started, we had different ways to have the remote side, which is the side on the microphone, where we could control how the microphone moved and how it sent data back to the soundboard side. We had the two methods that we came up with was using hardware to do all the comparisons and to determine which distance was the closest. And then the other option that we had was using software and a microcontroller to do the same thing. For the data transmission method, we said that we could either use wires and just run the wires just like the microphone cables all the way from the microphone back to the soundboard, or we could use some type of wireless method to do that. So what we actually chose to do is then using hardware to control the stepper motor, the distance gathering and everything for the remote side, and then we chose to use wireless communication to relay the data back and forth. So here's the block diagram for our project. The green side is the remote side, which is where the microphone is at. It just houses all of the comparator, the distance locator, so you can see if you turn it around, there's sensors in front of it. All of that, everything in that box is in the green remote unit. The XB communication network and the wireless communication network is the data transmission between the local and the remote sides. And the red side is the local side, which houses the system manager, which is the microcontroller that controls all data data comparisons to mute and unmute the circuit, and actually controls the GUI that we created. This is the technology stack diagram for the local side. So the entire thing, we called that the system manager, and then it had two different sections inside of that. We called the user interface, which is kind of like the GUI, and then the critical data I/O, which is the mute controller, and XB, which is actually how it gathers data from the remote side And then the mute controller is actually data that it has to switch so that it can actually mute and unmute the audio. On the user interface, there's two parts. There's inputs and the display. The inputs is how we actually gather data from the touchscreen, and then we can process it further. The display is actually the GUI that we created for the project. The remote side is, we ended up using software because the hardware was just giving us issues. So the technology stack diagram for the remote side, we just called that microcontroller the sensor manager, and then the two different parts that it had under it were data transmission and local interfaces. Data transmission obviously was the data being sent back and forth between the sensor and the system manager. Local interfaces was the controls for the motor drivers and the distance arrays. So this is our division of labor. Look through that. Jacob handled the power supplies, the mute controllers. I did the system manager and then all the most of the software associated with that. Mike did the XP setup. He actually made all the, had a 3D printing all designed up. And then Kalen worked on the comparator and the stepper motor. So the safety concerns that we have for our project is there's obviously 120 volts to power the local side, because it's just, to have everything powered, it was just easier to just pull in 120 instead of using the battery and just split it all out. So we didn't have to worry about current limits. When the microphone is moving, there's moving parts obviously, so if you get your finger caught in there, you might get pinched. It's not really major, but it's still something that's usually listed. And then some of the devices can get hot if they're running for a while, so it's just not. The risk management, we had 4 high-risk items that we had to create. Was the power supply, which was just how we supplied power to the microphone, all the sensors and everything in that one. So if we determined that it was not able to run the microphone for 5 hours as a stated goal, we would have to back up and use a AC power adapter to supply power. The other one was the comparator, which we started out using hardware again, and then we had to decide if that wasn't going to work. We had to decide if we were going to be using a microcontroller to do that, and obviously we did have to use that. The proximity sensor was just how we acquired the distance data from the remote side. We didn't really have a backup plan for that one. It was just kind of whether it worked or it didn't. So that was kind of a big deal. Then the system manager, which is the control for the GUI and the mute, unmute circuitry and everything like that. It also didn't have a backup. It just didn't have to work, but it was entirely software. So there was just multiple different ways that we could have done it. So, but it's still all software. So we didn't actually release the backup plan for that. So our actual implementation that we did, again, used software for the comparator because the hardware, we could, in the time that we had, we could not actually develop hardware to do everything that we wanted it to do. And then we also used XPs for wireless communications, as stated. And then originally we wanted to use infrared LEDs to acquire the distance data. And then once we got further into the project, we determined that that wasn't really going to be feasible. So then we switched back to ultrasonic sensors to actually acquire the data. Now here's Mike to do the cost estimate.
So we started out estimating the cost for all our parts. We ballparked it somewhere in the neighborhood of $550, depending on manufacturing and buying in bulk and possibly using, now knowing what we know of the sensors, possibly using a slightly different sensor could drop costs there, maybe down as low as $350. Our labor costs, we estimated up to $500 for labor and raw materials for the case design, the screen cover design, and there's this little adapter piece that's in between the case and the microphone for those. And then also another $450 in labor for our prototyping layout, implementation, software design, testing, packaging. So after all this was done, with that cheaper production cost, we thought we could maybe have a retail version for around $600. The other things that are on the market that he mentioned, we had the proximity gate, we had the just sound-based gate. None of them really have the flexibility that our solution provides. Also, ours adds some other features that aren't available elsewhere, like rotating the microphone, for instance. We think those justify the increase in cost. Here's our timelines. Not a whole lot to say. All of our dates, we stayed within 1 week of our projected time. Most of them we were early. I know there was one piece on the hardware one that I had a delay in my shipping of the proximity sensor, so it was a little later than I thought it would be. But everything kind of lined up where we had planned it to be. There weren't any real big hiccups. So returning to our goals, our first goal was by October 25th, we wanted to have up to 90 degree, or at least a 90-degree rotation. And when we measured it, it was 92, with 46 on either side of the center. So we met that goal. So we could go on. Our next one was the turning on and off the mute within 1 second of the user either being in or out of the range. And we used video frames, 30 frames per second, and then it was within 7 frames that triggered it both ways, so we met that goal. The distance values, we wanted them to be within 10% of the actual measured distance in inches. All of these distances were within 10%, but we noticed that offset would scale the further away. So the closer you were, it would be much closer to the actual value, but as you got further away, that offset, that error would grow with the distance that we're moving from the microphone, which was actually all part of the specifications of the ultrasonic sensor, so that all seemed reasonable. Our health and safety was to make sure that everything on the remote side was enclosed, no exposed circuitry. You can tell by a visual inspection that there are no, well, the battery is loose, but we have a revision where the battery's enclosed. Anyway, the battery is contained enough where you can't shock yourself. The leads are all covered and you can't shock yourself. And as for the user side, everything, all continuity was verified on all the grounds. Everything is reaching the earth ground, so everything looked good there. Our manufacturability, we wanted our battery on our remote side to last at least 5 hours. During our tests, we made it past 8 hours and stopped measuring after that. We thought 8 hours was a good stopping point because most wireless microphones actually die at about 8 hours. So we didn't really feel the need to go past that. So our environmental was to have a total weight less than 10 pounds and that everything would be ROHS compliant. Our remote side is less than a pound at 0.94, and then the user side was right around 9 pounds, and then all components were verified to be ROHS. Our economic goal was just that our total cost of all the materials would be under $550, and our total bill was $512 and some change. I'm going to hand it over to Kalen for a little wrap up.
So overall, we succeeded with all of our goals. We made the project work the way we originally intended. We helped to solve some existing industry gaps in their equipment, and we made it easy to use through the touchscreen and made it easy for the general public to use it. We had a flexible market where that it could be used by many different users, and any sound engineers or production people could run it. Let's go to the next slide. Our ABEC considerations, where we had health, environmental, safety, manufacturability, economics. We passed all of those goals. We were looking for to keep it in price range, keep it safe, keep it something that everybody could use, even if it was easy to use, it was safe to use. And then we kept it at a relatively low cost, and we assumed that there was an entire sound system already functioning and set up. Like I said, it would require a sound engineer to get all the connections made initially, but once they were made, it could be set up and left and run by just about anyone. Let's go ahead and go to questions.
So we
Demo demonstration first.
Yeah.
So we've got some pictures because our screen is a little small, and I know you guys want to be able to see it.
So for the GUI that we created, as you can see, we'll duplicate it up here so everyone can see it. See over me. So from the beginning, it gives the title of our project, and then it's just a quick, if you touch the screen, it will continue on. So whenever you touch the screen, we'll go on. This page is not displayed on here because this is a modification that we made as requested by Mr. Fischer and Dr. Zare to actually give default values so that you can skip all the setups. But if you select, if you do not want to use defaults, we will continue in to where we can select all of the colors for the screens. I don't remember which ones we used in the pictures, but so I'll just have to do it on my own. So whenever you go through all of the pictures, you come up with a display. It's ask you if that's an acceptable color for whatever your situation or just your preference. And then if it's not, we can go back and we'll start over again. I'm just going to do the same ones again. And then if you hit yes, we will continue on to where we can actually set the mute threshold, which is the distance from the microphone that we will actually cut the audio out. And then the arrows you can see there, you can just push up and down the arrows and we will adjust the number that's displayed there. Then once you press set, we continue on to the next page, which is the mute switching time, which is just kind of to protect the hardware. Again, this is one that we probably could have omitted, but for a more experienced user, you might want to be able to adjust the time for the switching time. So once you hit set, you continue on. And so from here, this is actually where we will test the hardware to make sure that the mute circuit is functioning properly. And then, so whenever we press mute, you have your audio playing.
We're gonna play a CD in the background so that
So you can actually actually hear everything how it works. So as you can tell, the music's playing. So whenever we press mute, we can see our LED triggers to say that we have successfully muted, and then obviously you can't hear anything, so it's succeed. So whenever you press next, we will continue on. And this is where we actually test to make sure the wireless communication between the local and the remote side is functioning properly. So to do that, we press test, and then it will send a signal to the remote side, and then it will send an acknowledgement to clarify that we actually have good communication between, which is shown here. The next button pops up once the actual acknowledgement has been received, indicating that the communication is correct. Once we press next, we actually go to our running page, which is shown here. The bar on the left is actually basically the current status of the system. The larger rectangular with the black inside is just the bar, just reference. We scale it, it shows 0 to 55 inches. So it's scaled. The blue bar inside actually is the current distance that fluctuates. You can kind of see here, fluctuating up and down as you move closer and further away. The bar that goes across the screen is the current threshold, and which just so you have an idea of how close the current distance is to the threshold. So as you see, when the bar goes above the threshold, the red LED trips, and if you do it here, sit back here. We also trip the audio to do that. So and then if you go back, step back in, and then once we go back, we unmute it, and so the green LED is on. So then from there, we can go in and set the direction, which displays a screen here, which has 5 motor positions, which correspond to the 5 different angles that we can actually turn the microphone in. So if we just go to 1, so this would be the far left screen. Yeah. We don't know, earlier it was working smoothly, so we don't know what's going on. We don't know what's changed yet.
the other way works just fine. Swing it back the other way.
Push. Yeah, so if we get set the direction and go back to 5, so it will swing smoothly across. So,
Fisher saw it work. That's all that matters.
And then, as you see here, before, if you remember, this third button down was just a blank spot. So when we have manual control of the microphone, it will actually, this button will appear. Once this button is pushed, and then the microphone is able to detect distances and actually move on its own without manual control. So then we can, we push the bypass button here. There it is. So when we can have a bypass button that we can actually, we can override all of our system and so that the audio is always allowed. Which, as you can see here, the distance is actually greater than the threshold and we still have audio play. There's also a safety feature built in so that if the actual unit was to lose power during the show, it would actually, audio is always allowed if the system is plugged in. And then from there, we can actually go in and from this screen, we can actually go in and change the threshold from the active running screen to a different distance. And then if we change it here, you can see that it will update the distance. And we didn't show everything on the pictures, but it will actually move this bar up and down as you scale. So in this,
And it will also change, it'll transmit that distance to the remote unit, and then it will change when it will, at what distance it'll pick it up to move the microphone, so that way they follow each other. That's the inside of the remote unit. That would be the inside of here. We have the XB, the motor, and then our proximity sensor array. And then the Arduino is underneath here. The motor driver to turn the motor is over here. We have a switch on the side so that we can power it on and off. And then the tail for the battery goes out on this side. And that's all we have. Any more questions? Or
How far is the wireless signal? So like how far can the microphone be from the unit and still pick up?
I took it to work the other day, and it went at least 75 feet, which was from the front edge of the stage to the back wall where the sound booth would be, the wireless transmission, and it worked exactly the same as it would right here. So we haven't found the maximum distance. We thought that it would go at least 150 feet, so 75 feet proves that. And then with a normal microphone, you would get about that distance. You would start to be approaching the limit of the wireless microphone to begin with. And the good thing is this receiver box could be put anywhere. It could be put on the side of the stage, it could be put in another room. As long as it has reception and it can get to our XLR cables for the microphone, we can place it wherever we need to. Does that answer your question?
I believe these were rated for 90 meters.
90 meters. Any other quick questions?
You have questions? All right, we'll go through here. Let's go to slide number 7, please.
just open it. Slide 7?
Yep. So I think on that slide, a figure would have been useful to show the microphone and then, you know, a zone in front of the mic or around the microphone to show kind of what the parameters are that you're looking at as far as the sensing. Did you have any kind of a requirement for rotation speed?
No.
Okay. Some performers are pretty animated, you know, they'll go back and forth pretty fast. If your microphone is real sluggish, right, it's never gonna keep up.
Yeah, and this was more, the thought was that it would be for children performers mostly, where you need to move this, or some single person standing at the podium, so that usually they would be in the same spot. But yeah, in the case of like a lead singer at a concert, that's why we put in the manual control, so they can override, tell it to stay still, or move it whenever they wanted to. But probably you just have it stay still for someone of that caliber. and then if they happen to be off to the side, then you can override and move it in. That was our thought.
Let's go to the 10th slide. This is just what we're trying to say, a nitpick. Titles generally do not have colons at the end of them. So subtitles and subtitles, don't put colons there. On the So on the manufacturability, I'm struggling to comprehend how battery life has a role to play in the manufacturing process.
I think our
How are
thought
you making
line
this?
was that if we couldn't do it with a battery, we're gonna have to do it with a power supply. And it was something about we wanted to make sure that it could run on battery.
Look at that.
Yeah.
So the idea for manufacturability is what process or how are you going to impact the manufacturing of this thing, right? Are you going to use computer-aided design of the circuit board so that you have, what's it called? Computer-aided, no, it's not right. I can't think of the acronym now. Basically, there's an acronym that talks about process, workflow for manufacturing, and you can make the manufacturing process better or worse depending on the choices you make with component layout and things like that. So manufacturing is things like, what materials are we going to use? Are we going to use connectors that have to be a human in the loop type connection, or can a robot make connections for the connectors when you have different circuit boards that have to be plugged together or something? Those are kind of the manufacturability engineering goals. Slide 15. So there's the top bullet item under resource. I'm wondering, it seems contradictory to a constraint. So a constraint is a boundary that is going to limit, in this particular case, right, a resource constraint is something like a backhoe, right? You're in a construction job, and you maybe have 3 or 4 different jobs going on and only one backhoe to share among those 3 jobs. Right, so that's a resource that has to be allocated at different times, to different jobs. If you have no such constraint, right, like you have list here, you have a plethora, right, unlimited number of resources available, how is that a constraint, right? I mean, it's kind of contradictory statement there.
Yeah, I think that's true. I think we just mentioned it to say that we're not using any like rare earth elements or anything like that, but yeah, it's not really a constraint. We were just saying that wasn't our concern.
Okay. Slide 16. Anytime you give references to the outside documents, make sure you give a complete description of the document or the reference. So don't say 802.15.4, right? Is that an ANSI standard, ISO standard, IEC, IEEE? Who publishes that standard, right? So it should be an IEEE 802.15.4. The other thing you should also include, again, this is a nitpick, but it should be the title of the document. Either IEEE 802.15.4, low power personal area network, or wireless personal area network, like low power WPAN. Same thing, uses 802.15, right? It's an IEEE standard. So identify the standards body or organization that publishes that standard. Let's go to slide 22. I mentioned this.
The chart.
Yeah. So on the computer, right, probably looks
Yeah.
great. On here, we got the old bulb that's, kind of been on for a long many hours and starting to wash out the colors, right? So anytime you do presentations, I always shoot for high contrast as much as possible color schemes, because you're guaranteed that the projector bulb on the system is going to be just kind of washed out colors when we do the projection. Let's look at the timeline slides, the 32 and 33. Typically, in like at the end of a production or prototype phase, there needs to be a comparison between the proposed and the actual costs, and the proposed and the actual timelines. Do you have a slide or any kind of way to compare the proposed timeline to what your real timeline was?
The way that our chart was set up, it was in week blocks, so it didn't push it outside. So we would have to have a chart that showed each day.
But I mean, you can use like color coding, or you have one band on another one, or anyway.
But they all overlap, is my point. None of them were,
Were
because
there
they were all
any-
within the same week, none of them.
Oh, okay, so there were no
Right.
shifts left or right in, okay.
There was nothing that exceeded 7 days, so we couldn't move it on the chart.
Okay, I got you. That's okay. Let's look at slide, so 35, what's I'm trying to figure out here, goal evaluations. Is 35 a custom, I don't remember, I'm not just looking, there's no label here to indicate this is a customer goal or engineering goal.
This was a
Customer.
customer.
Because
That's
the
still
ones,
part of the customer.
the ones later are labeled.
Ah, so I got you, okay. Now, the switching time measurement on 35, that was another question I had. So can you tell me again how you measured that?
So it was hard for me to tell when a person, visually it was hard to see when a person got into the range, and it was hard to time it with the code, because then it took into account the processing time, not the actual real world clock time. So what I did was I had someone stand out of the range, like as close as they could, where they started tripping it, and then I got them right below, and then I started recording the video, and they jumped up, and then I watched the frames go by, and I watched the timestamp, and then when it muted, or when it turned the microphone on, because I had the person in the frame with this and the LED, so I watched the timestamps on the video.
Okay.
I mean, that was the best, because I tried to do it other ways, I tried to do a stopwatch, but then I wasn't really sure when someone jumped in, so it was kind of a unique way, not a unique way to do it, but it was a unique situation. It was really hard to time any other way.
Okay. All right, I think that's all I got. Do you have anything else?
Yeah, I guess I do have a question. So I'm looking at slide 8, 7, and 8, I guess, for the goals. And so you have measurable goals on slide 7, and then slide 8 you had this observation of end user interacting. Did you do
Yeah,
any of that?
I ran, they were long videos that were, 15 minutes long of different people using it. I had different people that were not in the know-how about audio engineering or anything like that, and I just said, all right, there's a power switch, try it, and I videotaped them attempting to use it, and they all seemed to be able to be guided through the right path, and then, some of the things that they didn't know, we added that default features, so then they could skip it. If they wanted to stop at any time, they could shut it down. But yeah, I watched several people work through it unaided by me, but I wasn't sure how to incorporate that in a way other than me just telling you that I did it. have a video if you want to see it.
How might you have more scientifically evaluated some of those? Have you thought about that? For example,
Maybe like a survey after they were done? Might give you more like
even more better than a
statistical-
survey.
Okay.
How might you evaluate an individual's performance? So what's normally done, that I've seen done, is you come up with tasks, specific tasks that the end user is supposed to perform. And then you give them the task, say, there's just a piece of paper that says, okay, I want you to configure the microphone threshold distance for 50 inches, right? And you have it in some preset state of the system, which might also be a good idea, right? Have a button in there that says system of presets or whatever, right? You just have some default configuration that you can always go back to. Right, and so then you hand them this slip of paper and says, okay, now set this to, the distance threshold of 50 inches, and then you say, okay, 3, 2, 1, go, stopwatch. And you measure how long it takes them to figure out how to do it, right? You do like 20 different people, and you get that time, that data, and figure out, okay, what's the average or median time or whatever. And that's the measurable quantity then that you can use, right? That's a hard data point that you can say, for our usability factor, we want the customer to be able to figure out how to do this task in under 15 minutes or whatever. And maybe even give them, be nice and give them a copy of the user manual or something, they can actually, flip through and figure out, oh, here's how to do the user measurement, go to this panel, touch this thing, hit okay. So that's a more definable, scientific method rather than, anyway. Okay, any other? All right, well, pretty good job. I think it turned out awesome, actually. So I think this has actually potential as a real product. I mean, it could get, if you can find somebody who's, just won the lottery recently and they're willing to fund a startup, this has potential, I think, as a product. Of course, you first have to get patents and stuff like that to kind of protect your intellectual property, but yeah, I think it's a pretty good idea overall. So good job, all right.
Group after this one.